Our next talk will be Peter Cheng, and he will be talking about cognitive modeling of interpretations of representations.
Okay, thank you. So this is work with Aaron Stockdill, Grecia, Garcia, myself at University of Sussex, and Daniel Raggi and Mateja Jamnik at University of Cambridge. So what I'll be talking about is a theory of representation interpretation for which we've got a notation plus also an editor that allows you to build models of interpretations. Okay. So interpretations here are of external visual representations, graph charts, or they could be user interfaces, say. So there's three reasons why I'm personally wanted to develop this theory. The first is I've been designing representations for complex, challenging, and informational intensive domains for some time. And here's some examples of the representations which I've designed over actually decades, I would have to say. So one of the things I want to do is actually have a method which makes it easier to try to get some theoretical prediction of how beneficial different representations are going to be. One of the things that we've found with the designing of these kinds of representation and then testing them on users is that we can get factor of 2 improvements in problem solving or learning by changing the representation in a way that's effective compared with the conventional representations which say a skew children are used to learn mathematics or electricity. And I've developed quite a lot of these, including on the bottom right here, one of the most recent ones, a diagrammatic system for propositional logic. And also over here is a alternative to the London Underground tube map. And what I'd like to be able to do is quickly be able to make some theoretical predictions or at least arguments as to why these are better, rather than just the intuitive sense that most people have when I describe these systems. They agree that they're likely to be useful. So representation design is one reason I think we need to have a theory of interpreting the structure of representations. The work with Mateja Jamnik, Daniel Raggi, and the other co-authors is on a project called Automating Representation Choice for AI Tools. Okay? And what we want to do in this project is to get an AI system to choose alternative representations for problem solvers of different abilities for particular problems. And we've been working on this now for about 4 years, and we've had a little bit of success. I won't talk about the formal side of the work which Mateja is heading up. I'll just mention some aspects to do with the cognitive side. And so what we've tried to do is come up with a framework of cognitive properties for trying to classify all of the different kinds of cognitive things that might affect representation use. And the way we've done this is to have identify different levels of cognition, alluding to Simon and Anderson's ideas about orders of magnitudes in cognition, and also granularity scales as well. And we can populate this with different kinds of properties. And some of these you might think of just as the complexity of the search space which you're looking at. Other examples are the extent to which the external symbols map to concepts. And in the ideal, this should be isomorphic. If you have too many concepts and not enough symbols, or too many symbols, then you start to create cognitive problems. Another issue which is lurks here is what kind of quantity scale are you using? Nominal, ordinal, interval, or ratio? And that can dramatically affect the nature of cognition that's happening. Okay? So what we've done in the what we call a rep-to-rep project is actually to try to calculate some of these things from simple descriptions of problems simple descriptions of the representations of the use of problems. Okay. And we've got a number of algorithms to try to calculate these cognitive properties, and further algorithms also then to combine them together. But one of the things about this is it's really rather crude, the way that this is done, and we really didn't have a good handle on what it is that the learners are understanding when they're using a representation. So it really is our best guess. So is there some better way to do this? And so to actually try to model more sufficiently what users of representations actually have in their minds is what we want to do. The third reason, and this is the one which is particularly pointed to in the paper, is that we have lots of alternative interpretations. Okay? It's a cognitive phenomenon which I don't think is sufficiently acknowledged in certainly modeling of cognition and studies of cognition. So here we have a complex graph. Okay, and so someone who's expert, say an economist who knows a lot about Cartesian graphs, won't just see 2 lines. There's all sorts of economic knowledge which is brought to bear, such as the intersection is a particularly interesting point and maps to where trade to and from this particular country changes. But there's also complex information such as the areas under parts of the graphs, the quantities of amount of financial exchange between countries. And so at a more trivial level, someone who's a student just learning about Cartesian graphs in the first place may simply just read this graph in terms of the coordinate system and individual points. Okay? Of course, as I've been describing this graph to you, your internal mental representation of this particular representation has been changing. Okay, so even the moment-to-moment reading of an external representation, your own interpretation is changing. So how do we capture some of that in a somewhat more systematic way than we can by waving our hands or having verbal descriptions? And that's the point of representation, theory of representation interpretation. So, of course, there have been previous attempts in the cognitive science literature to try to talk about what kinds of structures we have in terms of that we're building when we're interpreting external representation. For example, Pinker and Kosslin have accounts from some time ago. There are also partial accounts picking out various kinds of cognitive phenomena which are of interest. So for example, Corinne talks about the importance of homomorphism in representations. There's also ideas about the use of schemas, diagrammatic configuration schemas, in terms of Codinger and Anderson's work on expert versus novice geometry problem solvers. So this is what's feeding into this theory. So to give you an idea of why we need this theory and the role of the theory, I'd like to make an analogy to, say, chemistry, early days of chemistry, where we knew there were elements which couldn't be atoms which couldn't then be further subdivided. Okay, so basic elements which can't be further decomposed. Then there are mixtures, materials, compounds, which are bulk substances. And in between, what makes chemistry so powerful is the idea that we have molecules, which are combinations, classes of combinations of different elements, which can then be used to explain mixtures overall. And it's this whole spectrum of the different kinds of theoretical entities that gives chemistry its power. And so what I'm claiming is that for thinking about the way that we use interpretations, this requires something analogous. And so a lot of the work on the effectiveness of representations tends to focus at the level of whole representations, our sentential, textual representations, better than diagrammatic representations. Another level at which there's lots of work is on what are the symbols and tokens and what are the syntactic rules for combining them. But what I think is missing is the sort of the middle molecular level. Okay? And that's one of the things, that if we can find common molecular structures of interpretations, this may well help us to understand the differences between different classes of representations. So what we've tried to do is to build into the theory various constraints. And I won't just describe these in terms of this verbally. I think it can be more interesting if I actually give you an example. So what we need to do is distinguish between the internal mental environment and the external representation. Okay, and out there, let's say there's a bar chart. You can obviously see the bar chart, and there may be words accompanying it, which, say, an instructor is mentioning. We also can distinguish another dimension, which is the represented world. So this is the domain of interest, where we might have concepts such as income, age, for this particular context. But there's also then the representing world. So these are the graphic objects, the things that you can actually perceive and see in external representation. And so what the theory claims is that there are specific types of schemas, okay, that will basically, whose job is to tie these things together. And so unlike other accounts of representations, the focus is on what are schemas whose function is related to representations, connecting the connecting the represented world with the representing world. And the idea is to build networks of these schemas, which then try to capture the structure of interpretations. What we claim is that there are 4 different classes of schemas that you need to consider. Representations at the highest level. Okay, so these are schemas for representations at the highest level. But of course, some complex representations actually have systems of representations built into them. So a simple bar chart will have Hindu-Arabic numbers built into it, or verbal labels. So there may well be sub-representations within a higher order representation. At the lowest level, there are symbols which are associated with graphic objects. So these are things that you could say point to in an external representation. We also identify R dimensions, which are sort of like variables. These are schemas can actually take different kinds of range over different R symbols. The key thing about each one of these schemas is that it both has something which identifies some idea or concept of the domain, plus also a graphic object associated with it. And this is at many different levels. And the final one is an R scheme, which basically are possible combinations of the symbols, dimensions, or even subdomains, okay, sub-representations. Okay, let me make this a bit more concrete by returning to this bar chart example. Okay? And so the whole bar chart, of course, is a representation. We have, say, the bars. So these are symbols, okay, R symbols, and there's 3 of them. Okay, and this combines information about the age and income of a particular class of individuals. Okay. And the whole class of bars we have a whole class of bars, and so we have an R scheme for the whole class of bars. And so in the model, we connect these all together. Also, there's more structure here in terms of we have axes. So there's the x-axis for age, okay, and also the y-axis for income and the concept of income and the y-axis. And so what we have overall is a coordinate scheme. So we have an R dimension which combines together these two, an R scheme that combines together these 2 R dimensions. We identify 2 kinds of links between these. These are hierarchical links between these different schemas. So what we would try to do in this, developing this theory, is to have sufficiently different sufficiently different schemas that will allow us to have the expressivity that we want, but not too much freedom for expressing things arbitrarily. Okay. Oh yeah, I'm got out of sync here. Okay, so there's these different kinds of connections, and there's two types, and I won't go into detail about the second one. The first one is just a generic hierarchical link. Okay, so this is the final overall model for this bar chart. So this is somebody who understands how bar charts work reasonably well. Okay. So what we want to do with these models is then to identify common patterns that exist across lots of different representations. Okay, and so remember this particular pattern of where here we have an R scheme, another R scheme, plus then these two R dimensions. Okay, and so this is basically a coordinate system that's working together, where we have the age versus income providing a coordinate system, plus then a set of bars which then fits into it. The editor basically allows us to build these models. Okay, and so this is fully implemented. You can easily fill in the various slots in the schemas that you need. Okay, so this is starting to provide useful information which you can then try to do interesting and useful things with. Also, there are numbers, there's support built into the editor to capture when you are not completing the model, not completing your models in a way that obeys the structure of this, as we specified the schemas. So what we're trying to build into the editor is essentially the constraints given by the theory. The way that we build models is to basically, for example, take a verbal description of a particular representation, and we then annotate it with all the graphic objects which are potentially of interest. Okay. And then it's then a matter of gradually then building up, perhaps from a top-down or bottom-up way, these networks. So here's a model of the Playfair line graph for someone who's fairly expert. And you can see at the top level here, we have a host set of these dimensions underneath one of these R schemes. And so there's a particular structure here. This is a model that we've built for from somebody who's less experienced, and you can see the structure of the model is much less complex for the person who's more intermediate in this domain than somebody who's more complex. And you can see here there is that structure which we saw earlier in the bar graph example. And so these common representational structures made up of certain collections of these schemas, we call idioms. Okay? And we think there are certain idioms which are common to a whole range of different classes of representations, even though they look really dramatically very different. We've built models for user interfaces. Here we have a PowerPoint toolbar, and it's been annotated. An expert's model, and you can see that's much more complex, much deeper than somebody who's less familiar with the PowerPoint toolbar. We've been quite nerdy in terms of our use of this, and I've explored UK registration plates in the Baroque way that the UK has over the years chosen to encode various kind of information in the registration plates. So there's a set of idioms. Okay, you can sort of get an intuitive sense of what they are from their names, and the ones which I've pointed out in our in the earlier examples are the explicit coordinate system, where you specifically identify a set of something which takes the role of a set of data, and there's also an implicit coordinate system where you have lots of different different R dimensions or these variables, and any one of them could serve the role as the set of data that you're interested in. So there's this possibility to shift your perspective that this is capturing. Let me just illustrate that these idioms we find across different representations. And so here we have that bar graph I showed you earlier, but this is a room numbering convention used at the University of Sussex, and it's pretty common. But one way to interpret this kind of indexing system is as a coordinate system of this kind. Okay, I won't go into the details of that, but this is something that we find quite commonly. So even though this is graphical and this is more textual or certainly alphanumeric representation, it has the same underlying functional representation interpretive units here. And so we're building into the editor the facility, and we can actually do this quite reasonably now, a way to identify these idioms and feed this back to the modeler. Okay, and so this can help the modeler do things like recognize that, okay, I've built this structure which I've taken from what I think the user of the representation is doing, and it then basically makes suggestions are, okay, is this actually one of the schemes, one of the idioms that has previously been identified? And so it can help with the model building. Okay. This is the example that appears in the paper, where we actually have a multi-level pie chart and demonstrate that there are various limitations to it. So there are various inappropriate codings of information there. And we've built models of this with different people interpreting that model. Okay, and what we find is you can start to read these kinds of idioms and also just the general structure of these networks in order to get some sense of how much information is encoded and how easy it will be to navigate the conceptual space given by a representation. So here you can see that we explicitly capture in these R dimensions the quantity scale that's being used. Okay? And so both for the concept from the domain, plus also the visual dimension that's capturing that concept. So here we have one where a ratio quantity scale is used for both the graphic object and the concept. And here there's a mismatch. One is an interval quantity scale, and the other one's a ratio quantity scale. Okay, and so this kind of information is then made quite explicit. It's also possible to identify where you have a single concept and many symbols in the external representation that corresponds to it, and so potentially causing confusion. Here also, of course, you could have concepts in your mind, but there's no graphic object associated with it. Okay? Or vice versa, there could be graphic objects out there, but there's no concept of the domain that relates to those graphic objects. And these are all situations that potentially can cause you cognitive difficulties when you're reading the representation. The latter case would be an example of just chart junk. And these kinds of ideas can be repeated not just at individual schemas, but also at a higher level where you have multiple schemas as well. Okay, so what we've found by building lots of these models is that there's often a lot of rich hidden interpretive structure when you're thinking about a representation. And this is perhaps not surprising. All of you will be familiar with using bar charts, and your knowledge is now really quite highly compiled for using a bar chart. Okay, and so if you are a teacher, you're thinking at a level of interpretation which is much higher than what a student would need. Okay? And so being able then to drill down and put yourself into the shoes of the learner is something that this kind of modeling might help you do. Okay. There are alternative interpretations have distinct network structures. Okay. And there are these idioms, these generic structures that we find across different types of representations, but the structures are the same. So these are like sort of representational molecules in that analogy. And so I hope also I've given you a sense that we might also be able to take the information which are captured in these models and start to calculate or get some handle on at least the potential difficulties of different cognitive properties of using representations. And so this is some work which you're doing at the moment, trying to turn those network structures and the content of the schemas into these kinds of measures. Of course, there's work to do to try and demonstrate the validity of the theory. Okay, we think that it's necessary, the schemas that we have are necessary and sufficient because we built lots of models and we haven't said, well, okay, there's another kind of schema, and certainly the 4 basic ones that we've got seem to be quite sufficient. And we're gradually building up a library of these different models of these representations, of different representations. Okay. We're starting to do work on doing further work on refining the model building criteria. Okay. And so this is leading into work which is also in progress. We're trying to do empirical evaluations of these structures, both with trying to get instructors modeling what they think their learners in different situations are using, but also thinking about using verbal protocol analysis and graphical protocol analysis in order to try and go straight from empirical data to these kinds of schemas. There's a range of different applications that we can imagine. I want to use these for representation design, but I think they could also have a role in a graphical user interface design as well. Okay. We're going to use them and are using them in the Rep2Rep project on trying to build this system to choose representations. And so it's giving us a much better foundation for trying to understand what it is that different users of representations actually have as memory structures. Okay, and of course, I think that there are a use of this for cognitive scientists before you actually start to build, for example, design a study. Perhaps you need to build these kinds of models so that you really have a much better handle on what are the memory structures when someone's trying to use a particular external representation. Okay. And finally, some acknowledgements. This is supported in the UK by the Engineering and Physical Research, Engineering and Physical Sciences Research Council. Okay, thank you.
I'll start with a question from Stephen Jones online. Could you elaborate on whether this work generalizes to also model human interpretation of other classes of stimuli?
Okay, it depends what you mean by other classes of stimuli. So in some ways, they are representations. If you're presenting somebody with a stimulus, something, it is a representation. And so something like the Ray figure, for example, which is used for looking at memory deficits, which is basically a line drawing, and you just draw it, and you're presented with it, and you're then given a certain amount of time, and you then have to memorize it and then draw it. Of course, it looks a bit like a fish. And if you hold the idea that it's a fish and you start naming the parts of it, okay, then that's really going to help you with the task of recalling it. Okay? Whereas if you're trying to remember at a lower level, all of the individual parts just as individual parts with no chunking going on, then of course it would be a harder task. So perhaps maybe that's, if you can give examples of stimuli, I could give a better answer. Hi, Pat.
Hey, so I like this work. I think it's very promising. I know you're coming from an educational perspective, but of course, representations have been an important topic in theories of problem solving, particularly on problems like mutilated checkerboard or problem isomorphs, right? Or older Gestalt stuff, right? Where it looks like people are able to solve some problems only when they shift their representation.
Yeah.
And it seems like your framework has potential for that, but it's hard for me to instantiate it. Can you fill in some of the dots, or you can even draw outside the box if you want?
Very funny, Pat. Okay. Okay, for something like the mutilated checkerboard problem, and I think it would be wholly applicable to try to use this kind of modeling for those kinds of problems. You basically have a different network structure where there are different kinds of salient things which are picked out in the model, and then relations amongst them picked out. Okay, so with a mutilated checkerboard, if you're thinking about using dominoes, okay, as the way to solve the problem, then of course you would then need objects for dominoes in these structures, and then how do they relate? And so I would say it's a representation. You have to interpret it. Different interpretations will give you different structures. And
how do you guide search through that space of representations?
Okay, so we're not searching through the space of okay, so you could think of the one of these models as a snapshot. Okay, and then these are some of the ambitions that we have. Is then that you could actually track someone as they are doing some problem solving, and as they mention different terms, you would build them into the model. Okay? And the idea, and we've already built in the functionality to capture the sequential development of these models. You could imagine perhaps partitioning up that trace and then say their productions here, okay? So that you could then start to model the problem solving. And wouldn't it be great if there were generic productions associated with the idioms, so that you could then get transfer from one representation to another?
A great talk, Peter.
Okay, thanks.
I wonder if you were familiar with the Tableau software?
Yeah.
Yeah, so that's it's for doing graphing and charts and from databases, and it has kind of a rough ontology of different kind of presentation types and what their intention is, taken from things like Tufty, and it seems like your thing might make a much better foundation for that. And at the same time, if you use that, the kinds of interfaces they have, then it would maybe satisfy Pat's wishes for a little bit more direct realization of it.
Okay, I'm not sure I understood the last point about direct realization of it. But okay, so one of the things, my frustrations with Tableau and those other those other tools for building visualizations is that they have built-in assumptions about what you can encode and how you can encode. And so I think certainly for the kinds of representations I design in order to try to get factor of 2 improvements in learning, you have to let go of all of those, a lot of those assumptions. So picking something which is effective for instruction isn't about, well, can we squeeze this data from this domain into a slightly different visualization? You need to be much more sensitive to what is the conceptual structure of the domain, okay? And how that then, how do you then encode that in a way that's transparent? And often you have to abandon standard visualizations. One of the reasons why they're so common, of course, is because they are general, not well tailored to the conceptual structure of a particular domain.
So you mentioned during your talk this notion of like, for people who understand bar charts really well, right? And bar charts are a simpler example, but something like this, or like the radar charts and so on. Do you think that there is a way to come up with a set of representations that actually helps a learner or learn how to interpret a particular complex visualization?
Yes, I'm sure that okay, so I want to go in 3 different directions with this, okay? One direction is, if I put my representation designer's hat on, I would say, actually, that's not a problem if you design the representation well in the first place, because it naturally scales with the learner. Okay, and so that you don't need to keep on introducing additional bits of notation to change the representation for new concepts. It's already packed in there in the first place. Okay, but I'm sure that you could design. Okay, so if you have a complex model, okay, and this is one of the things that we're thinking about how teachers might use this for designing pedagogy. Is you build a fairly complete model of some complex representation that you want learners to learn, okay? And then you can then start to target, what have I covered in my instruction up to this point? And one of the things that you find with instructors is that it's so compiled, the knowledge is so compiled that they forget to mention certain things. So I'm always saying to my PhD students, tell the audience what the axes are. Okay, you know what they are, but the audience don't. And on a larger scale, you can think of more complex idiomatic structures which are in representations that, okay, you need to cover all of these so that the audience knows how to interpret a representation, because if you don't tell them how to interpret the representation, they will surely interpret it in a way that you didn't intend them to interpret it.